Hello, everyone. Today I present my thesis entitled Functional Data Regression with Prediction and Interpretability, Property Inference in Chemometrics with Sparse Partial Least Squares. It was a pleasure to be working under the supervision of my director Clément Marteau and supervisors François Val, Laurent Duval, and Rami Al-Haddad, and also to be working in the University of Claude Bernard Lyon 1 in a co-tutelle with the St. Joseph University of Beirut and in a collaboration with IFPN. I thank the jury and of course my supervisors and every person that gave me any kind of support and help during these 4 last years. With pride, I share my findings and contributions to the field of functional data regression and chemometrics. With the diversity of this thesis background, we have been able to explore various aspects and generate valuable insights. The contributions align with the conventional data analysis scheme, and thus, I began this presentation by proposing a 6-step framework that generalizes the workflow of a data science project. This thesis takes place in the field of chemometrics. Relying on the definition given in Chemometrics and Intelligent Laboratory Systems, the leading journal in this field, chemometrics is the chemical discipline that uses mathematical, statistical, and other methods employing formal logic to design or select optimal measurement procedures and experiments, and to provide maximum relevant chemical information by analyzing chemical data. Next, we will roughly detail how each step can be completed, and more specifically, in a chemometrics context. Step 1, field-related and statistical context. In a data science project, it is crucial to understand the main context. Asking a set of measurable and clear questions, one can effectively identify issues and define primary objectives. Now, in the domain of chemometrics, key areas of focus include classification, pattern recognition, experimental design, signal processing, and multivariate calibration. Step 2, acquiring and collecting data. Data can be collected from both internal and external sources, and meticulous data collection is essential to uphold the integrity of the study, and quality control measures play a crucial role in ensuring data accuracy. Databases related to chemometrics are specifically designed to store chemical information. Some examples might be spectroscopic data, chromatographic data, sensor data, and others. Step 3, cleaning and pre-treating data. Data originating from various sources often exhibit dissimilar formats, types, and unique characteristics. To safeguard the integrity of the project, it becomes imperative to identify anomalies and eliminate duplicate entries. In chemical analysis, the data are often large and common issues can emerge, like outliers that can affect the analysis or missing data. We might want to do a normalization or baseline correction or even spectral smoothing. Step 4, evaluation strategies. This step depends on the objective already set. At this point, we organize an evaluation strategy based on our project goals. For multivariate calibration, one is often interested in assessing predictions, and thus he might be interested in computing error metrics, do calibration and validation splittings, and choose reference methods to improve. Also, he might be interested in the interpretation of the results. And so he can do this by evaluating localization, looking at the regression coefficients, and even testing sparsity. Step 5, analyzing data. This step allows manipulating data to extract meaningful insights. There are 4 main categories of data analysis, and chemometrics covers them all. The analysis might be descriptive, identifies what has already happened, Diagnostic, understand why something has happened. Predictive, estimates future bearings based on historical data. And prescriptive, provides future guidance. Lastly, step 6, algorithmic improvements, benchmarking, and dissemination. When all the previous steps are completed, at this point, it's time to share the results and the contributions. Therefore, this presentation will detail briefly the main work of this thesis with this following outline. First, we are going to set up the context, the chemical and statistical one, means you are going to clearly define our questions and objectives. Second, I'm going to present the data that we are dealing with, real and simulated. Now, the pillars of this work are two main methods. On the one hand, the calibration and validation splitting technique called calval-Xi, and on the other hand, the sparse regression method called dual-sparse partial least squares, dual-sPLS. And lastly, before concluding, I'm going to present a small demo of the methods that we gathered in our package called dual.sPLS. First important step is setting up context. In analytical chemistry, we deal with complex mixtures, and it is essential to understand their composition and their behavior in order to develop new materials and technologies. For example, in the oil field, we talk about heavy petroleum products that must be refined in order to be operative. Therefore, we focus on characterizing them. For instance, we can look at the global physicochemical properties. The most commonly used macroscopic properties are density, refractive index, and viscosity. However, the reference analyses that are currently employed for characterizing chemical mixtures are expensive and resource intensive. And so, rapid analysis is therefore needed. These methods are also based on the physicochemical aspects of products. We can evoke a vast popular method like spectroscopy, which includes nuclear magnetic resonance, NMR, infrared, IR, X-ray, and others. Their common thread is their signal profile represented by functional data or spectra. And the advantages of these approaches include miniaturizing, inexpensive running costs, and rapidity. However, rapid analysis is an indirect method for characterization. It is therefore necessary to resort to chemometrics techniques and develop predictive models for each physicochemical property using spectral information from the rapid analysis. And therefore, the focal point of this thesis relies on two main objectives. First, predict properties of novel mixtures having previous knowledge of reference one. And second, provide additional insights on the signal parts that drives the majority of the property. In order to achieve these goals, we resort to statistical methods. Resulting spectra from physicochemical measurements are classified as functional data. This figure here represents one NIR spectrum. It measures the absorbance of the mixture at different wave numbers. Problems like ours are usually solved by using multivariate calibration techniques with predictive analysis where regression modeling is mostly used. It operates by conceiving a mathematical relationship between explanatory data, which are the spectra, and response data, which will be the macroscopic properties. The set of physicochemical spectra are represented by this matrix X with n rows, which are the n spectra, or we might also call them observations, and p columns, which are the wave numbers or the number of variables. The physicochemical property, on the other hand, is represented by a vector y. Its dimension is n for the number of spectra, and our aim is to build a mathematical link between the response y and the corresponding matrix X here. We focus here on a linear relationship between the two compounds, transcribed by equation number 1 right here, where we have epsilon, that is the measurement error depending on the variability within the sample. It is expected to be independent of x with 0 mean. Parameter beta describes the relationship between x and y and should be estimated especially to understand the effect of each covariance in x on the response to y. This equation also allows to predict new responses related to external observations. Ordinary least squares is a common technique for estimating coefficients beta for the linear model 1. It aims at minimizing the sum of square differences between the observed and predicted values. More formally, it estimates beta with this equation number 2 right here. When the number of observations is larger than the number of variables, and the provided matrix X has a full column rank, the solution of this optimization problem is represented in equation 3 right here. Now, in our context, physicochemical spectra, represented by matrix X, are often represented by data with large number of variables and relatively fewer number of observations. In this context, ordinary least squares estimation fails due to this matrix here. Although it is a squared matrix of p dimension, its rank is lower than n, which makes the optimization problem too ill-conditioned and singular. Thus, other methods are required. These methods should, of course, help us to reach our goal set at this point. To identify them, we have to understand what kind of data we are manipulating. And this is why the second step of this presentation is understanding the chemometric data that we are dealing with. Two types of data were used in this thesis, real and simulated. On the one hand, real data ensures the study is valid, reliable, and applicable to real-world situations. And on the other hand, simulated data allows testing hypotheses and models in a controlled environment and explore different kinds of scenarios. The first contribution of this thesis was setting up the NIR real database as open source for it to be used and explored with benchmarking in other studies. A complementary data paper will soon be submitted in the journal Data in Brief. Several internal data sets were made available by IFPN. For confidentiality issues, we will only present the one we called DNIR. It contains two sets of information. First, it provides the density of 208 petroleum cuts. This physicochemical property plays a critical role in identifying the mixture functionality. Second, near-infrared spectra of the same 208 cuts are also included in the data DNIR. It measures how much near-infrared radiation a matter can absorb. Now, NIR spectroscopy provides insight about the molecule atom bonds. These types of data are often affected by trends and noise that seem unrelated to property of interest. It is thus essential to first remove artifacts and apply diversity enhancement operator. We used here the smooth derivative via Savitsky-Golay filters to do so. The 208 different pre-processed spectra of the data DNIR are represented in this figure on the left, and the number of variables are 1,557. As sometimes open source data are incomplete or unreliable, we developed a data simulator allowing us to mimic different behaviors observed in chemometric high-dimensional functional data. It will provide a simulated matrix X and also a simulated vector Y. For matrix X, each row n of independent matrix X, for each row of the independent matrix X, we will mix k Gaussians that have the same scale and randomly generated locations and amplitude A and K. So each spectra of X will be represented by equation 4. The resulting mixture of n Gaussians will be discretized using a uniform sampling in p variables. For example, a simulated data that we call DSIM is generated for later applications, and the number of observations we chose to be 300, and the number of variables 1000. Now for the response Y, first, as we consider linear regression context, we emulate the response to be linked to the matrix X with a linear combination of the variables of the matrix X with a preset uncertainty epsilon. This will allow us to evaluate the prediction performance. Second, our aim is to evaluate models beyond prediction accuracy. Model interpretability is closely linked to sparsity, particularly in the context of high-dimensional data. And sparsity refers to a situation where data contains many variables that have little to no impact on the outcome of interest Y. Thus, response Y here is simulated by imposing a small number of positive weights in the linear link between X and Y, and the rest will be null. For the construction of Y, in, for example, the data DSIM, represented in this figure right here, the variables in the red areas will be accountable in the construction of Y, which means we already know the localization of the information related to the response Y. And additionally, we also know which are the unimportant variables for the prediction. So until now, we have set up the context, clarified the objectives, we acquired data and pre-treated them, and now it's time to set up an evaluation strategy. In the next section, we will talk about our second contribution, which is a calibration and validation splitting technique that we call cal-val-xi. The associated article will soon be resubmitted. In this section, we focus on assessing the power of prediction of the conceived model. Calibration and validation splitting is commonly used to do so. It is based on splitting the observation into two sets. First is the calibration set. It is a representative set needed to set up the model by estimating parameters or coefficients. Second, a smaller similar set named validation is essential to estimate the quality of the final model. Several calibration and validation methods have been proposed in literature. We evoke here, first, the simple random sampling, which chooses calibration randomly, and each observation has an equal chance of being selected. The Kennard and Stone algorithm, also called CADEX. In a few words, it first selects 2 points that are the furthest away according to the X space, and then iteratively adds on the observation that is the furthest away from the previously selected ones. And a new method called split, it merges X and Y together, and it is based on a nearest neighbor search. Our objective, when conceiving the cal-val-xi method, is to provide a splitting method that improves the performance of these three splitting methods while providing an additional qualitative description of the data. In particular, our aim is to take into consideration not only the information in X, but also the information in response Y. Cal-Valzai was mainly based on the Cadix algorithm. Overall, it provides consistent, favorable results, indicating a better calibration coverage of considered databases. For example, here, we show the results for computing the ratio of Euclidean distances, which evaluates the similarity between the original and the calibration sets. It does so by computing the ratio between the sum of distances between the calibration points and the sum of distances between the overall set of points. Larger values of this ratio indicates increased repulsion between selected points and thus a better representation. Splitting was applied on 100 simulated data of the kind DSIM, and here we can see that both Cal-Valzai and Cadix significantly stand atop split and random sampling, although they both provide close performance. We notice a slight advantage of the Cal-Valzai in terms of quartile locations. This may hint at a more uniformly spaced design, slightly better representing the overall population, with observation as far away as possible from each other, using both X and Y. Now let's have a look at the Cal-Valzai algorithm. First, it is an iterative algorithm that selects one calibration observation at each step. It requires several parameters to be set. First, we define V to initially denote the set of n values combining X and Y in an ordered couple. Then we have the set NC, which is the number of calibration points desired. And then since Cal-Valzai is based on the computation of distances, an appropriate distance must be selected. So let dx represent a distance function restricted to the x space, which means it computes the distance between the x values of observations. And finally, a measure of the central tendency of a finite set of points must also be chosen. For the next example, to better understand the Cal-Valzai algorithm, we will apply it to an example, and we will choose a distance to be the Euclidean distance, and the measure of the central tendency will be the centroid. We chose a factorial design of 25 observations represented by two variables in X, X1 and X2. In this figure, represented in this figure on the left. The response vector on the right, in the figure where we represent the response variable, we can see that each of these values are the response value to the associated number of observation aligned with its location from the matrix X from the figure on the left. Step 0, response vector Y stratification in K classes. Stratifying is done in the Y space. Values of Y are first sorted, like in this figure on the right here, in an increasing order. Then the interval between the minimum and the maximum values of Y is split into sub-intervals, and here we choose 3. Thereafter, each observation is assigned to a subset VK. Step 1, starting calibration point selection. We choose the central tendency here, as I said, to be the centroid, denoted C0. It corresponds here to exactly the observation number 13. So the first calibration point is chosen among the furthest away observation from observation 13. And according to the Euclidean distance, we have 4 candidates: 1, 5, 25, and 21. We choose the one with the smallest index, so we choose observation number 1 to be the first calibration point. Second step is repeated iteratively. The next points will be chosen iteratively by first positioning the search in the subset that comes next from the observation that was selected, and then choosing the observation from the set that is the furthest away from the calibration set. In this example, as observation number 1 belongs to the first subset, we will position our search in the second subset, so the points in red. And we will search for the point that is the furthest away from calibration point number 1, which is observation 1, and that also belongs to the second subset. So here it is observation number 25. Now, so on, we do the same. We consider subset number 3 because 25 belongs to subset number 2. And we select observation 13, which is the furthest away from the 2 already selected calibration points, and so on until reaching the number of calibration points desired. After setting up an evaluation strategy, now I will present the third contribution of this thesis that is included in the 5th step, analyzing data. It's called dual-sparse partial least square regression, and it was introduced in an article published in Chemometrics and Intelligent Laboratory Systems. Let's recall the context. We have a set of observations represented by a set of spectra stored in a matrix X that we would like to link to the response variable Y. In a regression context, we usually resort to ordinary least squares estimation. However, here the data we are dealing with are high dimensional since the number of variables is bigger than the number of observations. Therefore, we have to resort to dimensional reduction techniques. They consist on converting data from a high dimensional space to a lower dimensional space while preserving most significant information of the original data. And we have different approaches that exist to do the dimension reduction technique. Most common ones are projection methods and penalized methods. Projection methods summarize original data matrix X by building a new space of lower dimension. A well-known projection method is the partial least squares regression. It is successfully applied in a lot of fields, especially in chemometrics. The PLS is an iterative algorithm. It is the tool that handles highly correlated data, and its goal is to search for M orthogonal directions. M is a number that is smaller than the P number of observations, and build a new space to which we will project the response vector in order to do the prediction. For in each iteration, one orthogonal direction is built. And it's built by maximizing the covariance between the response vector Y and the new component XW, subject to a norm 2 of W equals to 1. And so we are reducing the dimension from a matrix of P variables to a matrix of M components called the PLS components. However, PLS sometimes lacks appropriate interpretability. So another way to perform dimension reduction is to resort to penalization. Penalized method constrained regression coefficients by using shrinkage for variable selection. One often resorts to the lasso algorithm, least absolute shrinkage and selection operator. It penalizes the regression coefficients of the OLS using an L1 norm. This allows shrinkage, which will induce sparsity and amounts on selecting the most important variables. It is, however, known to be sensitive to data types. It does not always yield interpretable coefficients. So, as PLS projection methods and lasso variable selection approach have both advantages that we are interested in, blends of the two have recent avatars called sparse partial least squares, where the PLS dimensionality reduction step is combined to the variable selection method of the type lasso. The associated problem, number 7 here, does that. As you can see, it still maximizes the covariance between the response Y and the new component XW, like we do in the PLS. And it adds a penalization of the type lasso, so of the type L1. The solution behind the optimization is based on the soft thresholding operator in equation 8. And this will induce the variable selection. In fact, this operator compares the value of the magnitude of a vector U to a parameter lambda and shrinks them in 2 ways. If the magnitude of the coordinate of U, vector U, is smaller than lambda, this variable is exactly shrunk to 0. Otherwise, we subtract lambda from its magnitude. And this is how the variable selection is done. The optimization problem number 7 is solved using different mathematical tools presented in the following articles that we are going to use when we will benchmark and evaluate our method. Now, inspired by these methodologies, we conceived a more generalized procedure that we called dual-sparse partial least squares. It relies on the dual norm of a chosen penalty norm where shrinkage is applied adaptively. We start with the definition of the dual norm. Let's suppose we have omega, a norm omega. The associated dual norm, denoted omega star, is defined as for any z in Rp, it is the maximum value of ZTW constrained to a omega W equals to 1. Now, why is this relevant? If we go back a few slides and we look at the PLS optimization problem and we compare it to the definition of a dual norm, one notices that optimizing the PLS function amounts to finding the vector W that goes with the dual norm of the Euclidean norm L2, where Z is equal to XTY. And this motivated us to evaluate different norm expressions that could be used as domain-related penalizations. We emphasize 4 types of norms. The first one is inspired by the sPLS. It is the combination of L1 and L2 norm. The second one, dual-sPLS GL, which stands for group lasso. It combines groups of measurements. It applies the pseudo-lasso to each group individually while constraining the whole set. The third one is dual-sPLS LS for least squares. It introduced a matrix N1, and it's applied when X is not singular. It penalizes the classical least squares directly, and its associated solution is recovered when lambda is equal to 0. And lastly, for now, dual-sPLS R, which stand for reach, and it deals with cases where X is singular and resorts to a ridge-like penalization. In this presentation, we will focus on the first norm, dual-sPLS L, for the pseudo-lasso. Its closed form solution also adopts the soft thresholding operator, where Z is equal to XTY. Here, Z, the magnitude of Z, are compared to the parameter mu, which controls the amount of shrinkage. Nu is denoted as the product of the two initial parameters, lambda and mu. Choosing the appropriate parameters is always a challenge. The first parameter, mu, guarantees the constraint imposed, so it is easy to be set, but the challenge appears when choosing the second parameter, nu. In this case, we propose to choose it iteratively according to the number of variables that we would like to keep in the active set at each iteration, which means we impose the number of zeros that we would like to have in the W vector for each iteration. If you look at this graph right here, where we present the cumulative frequency of Z, which is XTY. If we impose at an iteration a percentage of 0 for the weight W, for example, if we impose to have 80% of zeros in the coefficient regression, we can easily find which parameter value of nu will allow us to get those zeros desired. This being said, we implemented this first case, and before applying it to our data sets, we used the following procedure. First, we benchmarked dual-sPLS pseudo-lasso against classical PLS, lasso, and the sPLS's avatars. Parameters were selected by cross-validation, except for sPLS Louna and dual-sPLS lasso, where we have to set a proportion of sparsity, and we chose a 99%. Then we split the observation into calibration, 80%, and validation, 20%, using calibration. And to evaluate the prediction accuracy, we compute the root mean square errors and increase the number of components from 1 to 10. And to assess the localization, we stack the regression coefficients for each compared algorithm and the original spectra. We first evaluate the dual-sPLS lasso on a simulated data DSIM. Our focus was on the impact of the number of latent variables on the accuracy of the prediction, which is the RMSE, of the 5 PLS-related methods. The two plots, clearly demonstrate the accuracy of RMSE that is improved, the accuracy of prediction that is improved while increasing the number of latent components. As we can see, the curves decrease when increasing the number of components for both calibration and validation. Now, the lasso performance is independent of the number of components, so we represent it with the 6th dotted line curve right here. Furthermore, as the number of latent variables increase from 6 to 10, all curves started to plateau, and their RMSE values became closer to each other. We observed that dual-sPLS lasso and dual-sPLS from shown in blue and the PLS in black provided the best results with the lowest curves among the 5 PLS-related methods. And based on this information, it appears that adding more components than 6 may not be necessary, and the optimal number of components lies within this range between 6 and 10. And this is why we choose 6 latent variables to compare the coefficient localization. We stack 7 panels. Original data in panel 1, the regression coefficients of the PLS in panel 2, the dual-sPLS lasso in panel 3, the 3 PLS avatars, panel 4, 5, 6, and in panel 7, the lasso regression coefficients. We can observe, looking at the second panel from the PLS, that the regression coefficients match the shape of the simulated data in panel 1. However, they fail to localize the most important variables. As you can see, we know that in the clear areas, there are unimportant variables, and this information is not deducted by looking at the PLS coefficients. And this is not observed in the sparse methods. To quantify the sparsity, we chose to compute a criterion called L0. It computes the number of non-zero values. And we found that dual-sPLS lasso, dual-sPLS Louna, and classical lasso have selected a small number of variables with an L0 value ranging between 40 and 60. However, this improvement in sparsity did not necessarily translate to a better interpretability. When we examine only the variables affecting the response in the red areas, we noticed that most of the compared methods showed significant coefficients in many useless areas. For example, in sPLS Louna, we have a selection of variables in clear areas. As for dual-sPLS pseudo-least squares, the selection is exactly done in the red shaded areas. And based on this, we can say that the dual-sPLS lasso provides a predictive quality compared to its challengers, and it is, according to this example, the best method in accurately localizing the important info. Now we will evaluate the performance of dual-sPLS pseudo-lasso on real near-infrared data. And we apply it on the data D and IR. First, for the prediction, we have similar conclusions as the application on the simulated data. RMSE curves in both figures on the left and on the right for calibration and validation globally decrease with an increasing number of components. Errors also plateau after 6 components, indicating that additional latent structure orders might be weakly helpful. Again, we assess model interpretation in this slide for 6 components. The location of the most influential features of the spectra. In this case, since we are dealing with real data, the localization of the important variables are unknown. But we might expect to we might expect that the most meaningful variables are located in the active signal parts, for example, right here. Now, if we look at the coefficients of the PLS, we can see that we can see that the presence of meaningful PLS coefficients is located across wider ranges, which makes it difficult to identify the specific spectral bands associated to the density, and which can lead to ambiguity. Now, all the sPLSs actually have smaller supports. sPLS from Louna and dual-sPLS least square pseudo lasso and classical lasso being the sparsest. If we look at the dual-sPLS pseudo lasso, we can notice then that the coefficients are smooth and contiguous, whereas for Shan, for example, and for Durif, they are more scattered, the coefficients are more scattered around, across the wave number axis. So overall, with these two applications, we can say that despite with these applications, dual-sPLS lasso still performs as well as competitors, even better in some cases, by looking at the prediction accuracy and the localization of the most important variables. So we can even say that dual-sPLS pseudo lasso found balance between a good interpretability and a accurate prediction. For the last contribution, the dual-sPLS method is readily available in R thanks to the dual.sPLS package. It is self-contained, including many functions that I will present right now. It is available in CRAN, and an associated paper will soon be also submitted in the Journal of Statistical Softwares. This package, dual sparse partial least squares, that you can find in CRAN with all the source files and the source codes and the reference manual. It has a list of functions. We have the regression functions, functions to predict, print, plot, and even the real data and the simulated functional data. To better understand how the package works, I will show you a small demo. Okay. First, installing the R package is we can install it in a classical way. We begin by loading it. We will apply the regression on the real data NIR stored in dsPLS.NIR. We store the NIR spectra in a matrix X and the densities in a vector Y. Then we will apply the calibration and validation using using calval-xi, which is stored in a function called dsPLS calval. We set the percentage of calibration to 70 and the number of subsets to split the vector, the observations using values from vector Y in 3. We can see here that this function will give us the index of the calibration observations and the validation observations. Now, this is a small plot that will show you the calibration points and the validation points. Then we store each set of points into two different matrices X and vectors Y. Now, since the regression model dual-sPLS is based on the number of components, a very popular method called cross-validation is usually used to choose the number of components. So it is stored in a function called dSPLS.cv, and it will help us to choose the most optimal number of components. Here it's 10. So using 10 components, we will apply the dual-sPLS pseudo-lasso with the function dSPLS lasso. Now, function dSPLS print will allow us to see how many variables were selected, the value of the parameter lambda, and the number of components for this. Now, if we want to assess the prediction and we want to compute the errors, there is a function called dSPLS metric that will compute the root mean squares, RMSE, the MAE, and the R squared. This small set of chunk of codes will allow us to have this figure where I compare the RMSE values to the MAE values. Then if we want to assess the localization, the function dSPLS plot will compare the regression to the mean of the original data by showing you where are the selected variables. And lastly, a very popular function is the function predict that will predict the response to a new set of observations, which are the validation sets, of course. We move on to the conclusion and some perspectives by recalling the 6-step procedure for a data science project. And we will point out in which steps we contributed the most and which steps can be taken into more account in some future related work. The main application of this thesis is the chemical mixtures characterization, linking physicochemical properties to rapid analysis by using chemometrics methods, more precisely multivariate calibration, and the main objectives were related to prediction accuracy and interpretability of results. I believe that the first contribution concerns step 2, where IFPN supplied us with the real data to support the study. And we were able to publish the real data as open source with a descriptive paper. And we also proposed a data simulator function. In step 4, we proposed the Cal-Valzai algorithm that chooses the calibration observation by taking into account both information from X and Y. With the conception of the algorithm and the results obtained, we proved that the associated calibration covers the experimental space as uniformly as possible and provide accurate regression prediction compared to reference methods. In step 5, to combine the benefits of both projection and penalized methods, we propose the dual-sPLS. This method uses a mix of the regression methods and applies shrinkage adaptively based on a dual norm of a chosen penalty. We proposed 4 types of norms inspired by state-of-the-art techniques. They demonstrate a balance between accurate prediction and good interpretability. And in this work, we also implemented all the concerned functions in the R package called dual-sPLS. We believe that other related work paths could be taken into account, starting by contributing in step 3. We have utilized several pre-treatment procedures, including Savitsky-Golay filtering and differentiation, to achieve these goals on real data. However, we are also keen to explore other treatments, such as wavelet treatments, which we believe can play an instrumental role in removing baseline, filtering, differentiating, and reducing noise. Wavelet treatment is particularly intriguing to us because it has the potential to reduce the dimensionality of the data by concentrating the information and enhancing data diversity. Additionally, we find that the wavelet filtering potentially is interesting to our problematic, as they often use shrinkage in their application. This figure here on the right represents a glimpse of our first tests. On the upper left, we show the first NMR spectra of a data that we had the chance to also manipulate. On the lower right, we show the application of a wavelet transformation of the time seam 4 at a decomposition level of 1. It reflects diversity enhancement, where information is concentrated in around the first 6,000 variables, and beyond this range, the transformation shrinks the rest of the variables to 0. The upper right plot represents only the first 6,000 variables after this transformation, to which an inverse transformation was applied to reconstruct the spectra in the lower right plot. And we can see how both spectra are very similar. Now, this treatment was repeated to all the spectra, the 93 spectra, in 5 levels of decomposition. We applied dual-sPLS to each of the 4 sets. Preliminary results seem to indicate that the transformation appears to effectively concentrate the information up to a certain level while respecting the positivity constraints of the data. In terms of prediction now, we have found that a more global decomposition of the data improves prediction accuracy and allows for a faster convergence to a stable number of components. However, there are still questions that need to be addressed, particularly regarding the location of the coefficients. Therefore, we found that it is worth to dig a little more in this direction. In the last step, we are interested in improving the study of the importance of the results of the PLS and the level of uncertainty associated with them. In our future research, we aim to assess the level of uncertainty in the first direction and corresponding component PLS, which indicates the degree of deviation from the true target. Our plan involves testing the null hypothesis and constructing confidence intervals. We were interested in Cook and Forzani's work, who investigated the statistical properties of PLS in 2017, specifically the asymptotic behavior of prediction using the first PLS component. They later developed their studies by moving on to the multidimensional components. Now we went through a slightly different direction, and we wanted to compare and analyze the efficiency of 2 nullity tests and determine which test provides faster signal information. The 2 tests were evaluated simultaneously. First test is for the first component W, where rho here is a real value, And the second test is for the first component, PLS component. We simulated several data and tested several values of rho. In this figure here, the red curve and the blue curve represents test 1 and test 2. It was observed that as the value of rho is increasing, both curves increase 2 and begin to plateau at a value of 1, which was actually expected. However, the red curve, test number 1, reaches an asymptotic value of 1 faster than the curve in blue, which is for test number 2. Also, when a value of gamma, dotted line right here, is fixed, for example, if we set gamma to 5%, we observe that test 1 requires a smaller value of rho than test 2, which allows us to say that the power of the test in red, the test 1, is stronger than the power of the test number 2. Which means that test number 1 has a stronger power in detecting the presence of information in the first PLS. In other words, it is more sensitive to smaller signal strength and can detect useful information even if the signal is weak. So these were the first few results concerning this part. We hope to contribute more, of course, to understand the statistical property of PLS. Of course, there are other subjects that can be considered, like other pseudonorms, or also the dual-sPLS group lasso, which was not really tested because we cannot find data with several lipid analysis spectra to evaluate this regression method and improve it. This is the end of the presentation. Thank you everyone for your attention.